Good morning, all. Today we are going to discuss about simulation of fan type of load. Right? So we know the fan type of load is one which is having characteristics load torque proportional to speed square, or should I say TL is some k times omega square. We also know that motor develops torque which is equal to load torque, and it runs at steady speed at which this equilibrium situation is satisfied. Tm is equal to TL. So what is different about fan type of load? We know that in case of motor torque is proportional to voltage square. If you're talking about induction motor, this is the situation. So when you reduce the voltage in stator voltage control method, motor torque also reduces. If you have a constant type of load, then motor is not able to supply that much torque at reduced voltage. But if fan type of load is there, with this reduction in speed, reduction in torque, the speed also gets reduced, and so the motor that is load torque now offered is also less. Once again, with this new situation, you can see you can have this situation Tm is equal to TL at reduced voltage, and so fan type of load can work with the reduced voltage, or stator voltage control method is good for fan type of load. Right? So fan type of load is okay with reduced voltage. Right? So let's see the simulation, and I would like to show you how the reduced voltage this fan type of load is able to cope or handle. Right? Now, what else we need to calculate first is that the motor what I have selected is 5 HP, and it is 1750 RPM, and radians per second is 183.16 radians per second. Right? So if from this I calculate my torque, rated load torque is coming out to be 24.44 Newton meter. Right? So with rated speed, motor is able to produce this much torque. So load torque should also be not more than that. So what is the situation over here now? That load torque maximum possible is 24.44, which is equal to k into omega square. Let's try to find k. So what is k? No, and omega is 183.16 square. So from that, if we calculate k, it comes out to be 0.000728 for my case, the model which I have selected. Right? So with this value of k, I would like to simulate my model. Right? Let's go to the yeah. So this is a simulation model which we had used in our previous video also. The only change is that instead of having constant type of load, I have given a speed multiplied with the k. This is nothing but k into omega square, k into omega. U1 is a signal which is fed back to this block, which is omega over here. So omega square into k is the output of this block, which is given to this point, this input, which is nothing but the load torque. At present, I am giving the rated voltage, and you can see 1 into square root of 2 into 460 divided by root 3 is the peak phase voltage which we have created. In this, if I have entered 1, because this is 100%. If I would like to apply 80%, instead of 1, I will change it into 0.8. Right? So let's see, now it is done. We are applying full voltage. We are expecting full speed and rated torque with this fan type of load. So this simulation of fan type of load with rated voltage and rated speed. Let's see the simulation. You can see motor is producing 750 RPM, right? 750 RPM is verified. Also, it is producing the rated torque, which is 24 plus 25.5 and some induction and other torques are also supplied. So that is specified in the inbuilt model. So it is producing rated torque and it is producing rated flux also, right? So this is good. Yeah. So motor is producing with the given function, rated speed and rated voltage. Now let's try to reduce the voltage to say 80%. And reducing voltage to 0.8 in all these three voltage blocks. As a result of which the motor developed torque will reduce, the speed will reduce, and load torque also reduce. So this motor, whether it is running in equilibrium or at steady speed or not, that is what we would like to see. Right? So we have saved this new value and uh, simulating the 80% of the rated. So you can see the speed has reduced. It has reduced to 1720, but it is able to run at steady speed, and it is producing the reasonably little bit reduced torque, right? Because the reduction in voltage is not much, but the torque is reduced, and noticeably the flux has also reduced, and that's why in V bias control method we also say that you simply cannot reduce the voltage at same frequency. If you do so, your flux is also going to reduce. Anyway, so this is the situation. Once again, I will change the voltage to say 50%. And a drastic reduction in voltage, so speed is going. Voltage is one half, so motor torque should be one fourth. So load torque also should be one fourth. So let's see at this situation whether it is running at steady speed or not. Right? The other things are same. Scale it. Okay. Once again, you can see at the half speed also it is running at steady speed. Of course, the speed is now drastically reduced to 1500 and 65 instead of 1750 because it rated speed. Its torque has also reduced to 20 instead of 25, and flux has also reduced. Right. So this is possible because this is a constant. You can say sorry. This is a fan type of load. If in this place, if I have a constant load torque, this motor will not run with this type of reduced voltage because the load is constant, say rated, and the voltage is reduced to half. So motor torque reduces to one fourth, and then motor is not able to produce sufficient torque, and so constant load type applications cannot run with reduced voltage. But when type of applications like blower, pumps, ship propellers, they all can run with the reasonably, you can say, reduced voltage. The stator voltage control method is also studied over here, and you can see that when type of application simulation is done, and you can run it with these variable voltage, right? So the simple simulation was targeted. We'll see more of it in our